Welcome to lecture 4 on properties of triangles. In the last lecture, we solved some problems related to the relations between the angles and sides of a triangle. In this lecture, we will focus on problems related to circles which are associated with triangles. For example, the circumcircle, the incircle, and the ascribed circles. So, before we set on to solving these problems, let us recap the important formulas. So, the first formula was the sine law, which is basically the ratio of the side to the sine of the corresponding angle, and it says that the ratio of the side to the sine of the corresponding angle is a constant. So, it is the same for all the sides. And then we also had the cosine formulas, which give the formula for the cosine of the three angles in terms of the lengths of the sides of the triangle. We had also derived the formulas for the sine and cosine of the half angles of the triangle in terms of the lengths of the sides and of course the semi-perimeter S. We will also be using the formula for the area of the triangle, which is given by square root of the product of S times S minus A into S minus B into S minus C, and this of course is equal to BC by 2 sin A is equal to AC by 2 sin B, and that is equal to AB by 2 times sin C. We also derived the formula for the radius of the circumcircle. So, if we recollect, the for any triangle the circumcircle is the unique circle which goes through all the three vertices of the triangle. So, let us say if the vertices are A, B and C, then the circumcircle of this triangle is the unique circle such that these 3 points A, B and C lie on the circumference of this circle. So, it will be something like this, of course. So, this will be the circumcircle. The radius of the circumcircle is called the circumradius. The center of the circumcircle is called the circumcenter. We also derived the formula for the radius of the circumcircle, and we had denoted it by the uppercase letter R, and we had shown that it is equal to the product of the sides divided by 4 times the area of the triangle. So, area, as you recollect, we have been denoting it by this Greek symbol delta, and we had also shown that the circumradius R is also equal to the ratio of the side of the ratio of any side divided by 2 times sine of the corresponding angle. So, it is equal to A divided by 2 sin A, which is equal to B upon 2 sin B is equal to C upon 2 sin C. We had also defined and analyzed another circle called the incircle. So, for any triangle ABC, for given any triangle ABC, there is always a unique incircle. So, the incircle is the circle which touches all sides at exactly one point. So, it touches each side at exactly one point. So, this is the incircle. The center of the in circle is called the in center, and the radius is called the in radius. The formula for the in radius, which we denote by the lowercase letter r, is given by the ratio of the area of the triangle to the semi perimeter, and it can be shown that this is indeed also equal to all of these other four equivalent formulas. And to prove any of these is not very tough, because to prove these we just have to use the expressions for the sine and cosine of the half angles. So, for example, it's very easy to show this first expression here. So, this is nothing but s minus a into sine a over 2 divided by cos a by 2, and then we take the expression for sine a by 2 and cos a by 2. So, tan a by 2 will be this quantity divided by this. So, this is therefore equal to s minus a into root of s minus b times s minus c over s into s minus a. And then by taking s minus a inside, what we get is that this is equal to square root of s minus a into s minus b into s minus c over s. But then we, from the hero's formula, we know that the area of the triangle denoted by delta is equal to this quantity, which already has this product of s minus a, s minus b and s minus c, and therefore this product is nothing but, so essentially by using this formula here, by using this formula into the expression here, what we will end up getting is that this will be equal to, this will be, we can show that this is equal to delta over s, and so that is what proves the first statement here. In a similar manner, by taking the sine and cosine of the half of angle B, we can also show that the expression, another expression for the in radius is that it is equal to s minus b times tan of b by 2. And again, this can also be proved in the same manner. We just have to replace this sine of these half angles by the formula that we had proved earlier, which is so we just have to replace those expressions for the sine of the half angles by these, and by this and this formula. So by replacing this sine by these expressions and taking the product, we will get r equal to 4 times r. Of course, we have to also use the expression for r that we just saw in the previous slide. And then we also defined and discussed the ascribed circles of a triangle. So, if we have a triangle A, B and C, then we do not have a unique ascribed circle. In fact, there are exactly 3 distinct ascribed circles. So, the ascribed circle opposite to angle A is constructed like this. So, we take the side AB and we produce it. Similarly, we produce the side AC like this, and then we take the angle bisectors of the exterior angle B and the exterior angle C. So, let these be the angle bisectors. Let us say that they meet at this point O1. So, then this O1 is essentially the center of the ascribed circle. So, the ascribed circle opposite to angle A is the circle which touches this line BC, and the produced part of this line AB and the produced part of this line AC at exactly one point. So, in this case it will be something like this, and the point where these angular bisectors meet will be the center of the ascribed circle opposite to angle A. So, by notation we define the radius of this ascribed circle which is opposite to angle A, we define the radius by r1, and then for the ascribed circle which is opposite to angle B. So, that will be obtained by producing this BA and BC and then taking the angular bisectors of the exterior angle, this angle. So, this is angle bisector and also the angle bisector of this exterior angle, and so this will become the, so this point will be the center of the ascribed circle opposite to angle B, and the radius of that ascribed circle opposite to angle B will be r2, and similarly the radius of the ascribed circle opposite to angle C will be denoted by r3. These expressions were derived by us in the previous one of the previous lectures, and of course each one of them can be shown to be, for example, for r1 we can show that r1 is also equal to s times tan A by 2. In many books and at many places you will also find that the radius, these different radius are also collectively called as the x radii, as the x radii of this triangle, x radii of the triangle ABC. So, collectively sometimes we collectively call these three radius as the x radii of the ascribed circles corresponding to triangle ABC. We take up some problems now. So, this is the first problem. So, it is said that in a triangle the sum of two sides is x and the product of the same two sides is y. So, let us say that these two sides are of length A and B, then we have x equal to A plus B and we have y as the product AB. The third side is of length C and we have this relation which states that x square, so A plus B is x square minus C square is equal to y, which is the product of the sides, so is equal to AB. It is asking us to find the ratio of the in radius to the circumradius of this triangle. So, the question is asking us to find this value, the ratio of the in radius to the circumradius, and the correct answer is one of these four options. So, if we recollect, this is what was given in the problem, and that can be simplified to A square plus B square minus C square is equal to minus AB. But we have already seen this type of expression. So, if we recollect the expression, the cosine formula for cos C is precisely A square plus B square minus C square over 2AB. But since the numerator here is equal to minus AB, this cos of C is equal to minus AB by 2AB, which is equal to minus half, and since C belongs to 0 to pi, cos C equal to minus half implies that C is equal to 2 pi over 3, or essentially 120 degrees. So, we have been so far able to find the value of this angle C. What we have to find is the ratio R by capital R. So, for this we have to use the formulas or the expressions that we have derived for the in radius and the circumradius. So, for the in radius we had the formula that r is equal to area divided by S. So, we can write r as area divided by S upon the expression for the circumradius was the product of the lengths divided by 4 delta, where delta again is the area. So, if we use these formulas here, what we have is that the ratio is equal to this quantity, which is equal to 4 times delta square over ABC times S. And then we can also use the we can use the expression for delta, which is the Hero's formula, or else since so when it comes to multiple choice, we have to be a little alert in basically trying to express this in terms of one of these 4 possibilities. What we see that is that the expression in the numerator is y, which is AB. So, all these options have y in the numerator. So, somehow we should get y, which is AB, in the numerator here. What we have right now is that AB is in the denominator. So, if we recollect, the one of the formulas for the area of a triangle was that the area is also equal to AB upon 2 into sine of C. And this is exactly the formula we should also use, because in fact we have already found the value of C, and therefore sine of C is a known quantity for us. Hence, if we substitute delta area equal to, so if we substitute area equal to AB upon 2 into sine of C, but sine of C is sine of 120 degrees, or sine of 120 degrees is square root of 3 over 2, and therefore from here the square of the area will be A square B square into 3 over 16. And by putting this expression over here, we get that the ratio r by capital R is equal to A square B square 3. So, we already have a 4 here. So, we will get 4 in the denominator, A B C times S, which is equal to 3 AB upon, so this AB square, and so the AB square and the AB in the denominator will get cancelled, and what will remain is only AB in the numerator, and this AB is y. So, we have been successful in getting y in the numerator only, divided by 4 times C times S. Taking it to the next slide, we had R by R equal to 3 times AB divided by 4 times C times S, which is 3y upon 4c into, now S is nothing but A plus B plus C over 2, because it is the semi perimeter, and therefore this is also equal to 3y upon 2c into A plus B plus C. But we know that from the statement of the question itself, we know that A plus B is x, and therefore this is x plus c. So, we finally have r by r as equal to 3y over 2c times x plus c, which is option B. Let us take the second question now. It is said that the x radii, which is basically the radius of the ascribed circles R1, R2 and R3 of a triangle ABC, are in HP. HP stands for harmonic progression. And then we are asked to show that the sides A, B and C are in arithmetic progression. So, since R1, R2 and R3 are in harmonic progression, it follows that 1 by R1 plus 1 by R3 is equal to 2 by R2, or 1 by R1, 1 by R2 and 1 by R3 are in arithmetic progression. We already know that the formula for R1 is delta upon S minus A, R2 is delta upon S minus B, and R3 is delta upon S minus C. So, by substituting these into this equation, what we eventually get is that S minus A over delta plus S minus C over delta is equal to 2 times S minus B over delta. So, delta is common to each of the fractions here. Therefore, what we get is that S minus A plus S minus C is equal to 2 times S minus B, and from here it follows that A plus C is 2B, or A. So, A plus C is 2B essentially implies that A, B and C are in arithmetic progression. So, this finishes the proof of the second problem. So, here is the third problem. In the third problem, we are asked to prove that the product of the distances of the center of the incircle from the vertices of a triangle is 4 times the circumradius times the square of the inradius. So, we are talking of an incircle here. So, let us say that if so let us say this is the triangle A, B, C, and we have these angle bisectors because we are talking of incircle. So, then this point here is the incenter, and therefore these are the distances. So, let me mark them in red. So, the distances of the point O is the incenter, and the distances of the incenter from the vertices of the circle is marked in red. So, these are the distances. Now, we have to take a product of these distances, and we have to show that it is equal to 4 uppercase R times square of the inradius. So, now since these are angle bisectors, it is clear that so these are half angles. This is B by 2 and this is A by 2, this is also A by 2, this is B by 2, A by 2, sorry, this is C by 2, and this is also C by 2. So, let us drop perpendicular from this from the incenter to each of the sides. So, this of course the length of this perpendicular is of course the inradius or the radius of the incircle. So, this is also R. This is also R. But then these distances need not be equal. So, these distances need not be equal. Let us now consider this right angle triangle ADO. So, from this right angle triangle ADO, we get that sine of A by 2. So, sine of this angle here A by 2 is equal to OD upon OA, and therefore OA, which is the length of the distance between the vertex A and the center of the incircle. So, this is the first length. So, this length OA from this equation it follows is equal to OD upon sine of A by 2, but OD is nothing but the in radius r. So, OA is equal to r upon sine of A by 2. In a similar manner, we can show that OC is equal to r upon sine of C by 2 and OB is equal to r upon sine of B by 2. And now the question is asking us to take the product of these three lengths OA, OB and OC. So, the product of these three lengths is given by OA times OB times OC equal to, and for that we use these three expressions. So, we may basically multiply this, this and this, and we end up getting r cube divided by sine of A by 2 into sine B by 2 into sine C by 2. But if you recollect, we have already seen this kind of a product of the sine of the half angles of all the three angles. So, the product of the sines of half angles. So, if we recollect the expression, so this particular last expression here also contains the product of the sine of the half angles. So, this is what we plan to use. In fact, from this relation that r is equal to this quantity, it follows that the product of the sine of the half angles is in fact small r upon 4 times uppercase R. So, we will replace this entire denominator by the ratio of the in radius to 4 times the circumradius, and therefore, this becomes equal to 4 r into r square, and that is exactly what was asked to prove in the question. So, this is what was asked to prove, and we have shown that the product is indeed equal to 4 into uppercase r into small r square. We now move on to the fourth question. So, in the question it is stated that there are three circles whose radius are 3, 4 and 5, and they touch each other externally. And let P be the point of intersection of the tangents to the circles and the point of contact. So, in this problem we have three circles. So, let us draw these three circles one by one. So, let us say this is the smallest circle of radius 3, then we have another circle of radius 4 centimeter. So, let us say this is circle 1, this is circle 2, and then we have the largest circle which is of radius 5 centimeter, circle 3. So, these three circles they touch each other externally, and let us say that these points Q, R and S are the centers of these three circles. Let us join these centers by straight line segments. Of course, from high school geometry we know that when two circles touch externally at a point, then that point must lie on the straight line joining the two centers. So, therefore, the point of contact of the two circles at this point is on this straight line segment R Q, and the same is true for the other line segments R S and S Q. Let us now draw the angular bisectors of all the three angles of this triangle. So we know that the three angular bisectors meet at a common point. Let this red dot denote this common point of intersection of the three angular bisectors of this triangle QRS. Next, let us consider this triangle. So let this point of contact be denoted by T, and let the point of contact between the circles 1 and 3 be denoted by A. So T is the point of contact between the circles 1 and 2, and let us join this T to this point. So let us denote this point by O. So we join O and T, and we also join O and A. So now if we know that since this dotted line is an angular bisector, these two angles are equal to angle R over 2. So these two angles are equal. Further, this side is common to both these triangles. So we are talking of the triangles RTO and triangle RAO. So we will show that these two triangles are congruent because they have a common side. These two angles are equal, and also that this side RA of the triangle RAO is equal to the length of the side RT of the triangle RTO. That is because both RA and RT are equal to 3 centimeter, which is the radius of this first circle. So this length is 3, and therefore these two triangles are congruent. And in a similar manner, if we can join this point O to, let's say that this point of contact of these two circles is denoted, let us denote that by point B. So this is point B, and we also join O and B together. So again, because this dotted line is the angular bisector, we have Q by 2, and we also have Q by 2 over here. Similarly, this angle is S by 2, and this is also S by 2. So just as we had shown that these two triangles are congruent, we can also show that this triangle and this triangle are also congruent, and therefore what we have is that this length is equal to this length is equal to this length. So these three lengths are equal. These three lengths are equal. Further, we also have that this angle and this angle are equal. So let me call this angle as x. So this angle is also x. And further, from the congruency of this triangle and this triangle, it follows that this angle, which is 180 minus x, is also equal to this angle, which is 180 minus x. But since this is 180 minus x, it follows that this angle has to be x. And then again, from the congruency of this triangle, so this triangle and this triangle can also be shown to be congruent in a similar manner, and therefore this angle and this angle has to be equal. And since this is x, this angle will also be x. And therefore we see that this x plus this x is a straight line, and therefore this angle x has to be 90 degrees. And therefore what we have shown is that the angle RAO is 90 degrees. So since RAO is 90 degrees, it follows that this line segment AO this line segment AO is actually a part of the, so this line segment AO is actually tangent to the circle 1 and it is also tangent to this to the circle 3. So, this line segment AO is a common tangent to both the circles 1 and 3. Similarly, we can show that since x is 90 degrees, it follows that these two angles are also 90 degree and these two angles are also 90 degree. So, since these two are also 90 degree, it follows that this line segment which is joining the this in center of the triangle QRS to the point of contact of circle 1 and 2. So, this point is at 90 degrees with the this line segment joining the radius, and hence this line segment is the common tangent to the circles 1 and 2. Similarly, this line segment OB is the common tangent to the circles 2 and 3. And we know that these and therefore these three tangents are meeting at this point O. Hence, this point O is indeed the intersection or the common intersection of the three tangents. In the question, this point O has been denoted by the point P. So, the point P in the question is nothing but this point O, and we have now seen that the intersection of these three tangents or the common intersection of these three tangents is nothing but the in center of the triangle QRS. And now the problem, if we recollect, the problem is asking us to find the distance of this point P from the point of contacts. So, the distance of this point P or O, however we call it, the distance of this point from the contact. So, this distance and this distance and this distance, we had earlier shown that all these three distances are equal. So, we have been asked to find this distance, but we know that since this is 90 degrees, we know that this distance is nothing but the radius of the in circle. So, it is nothing but the radius of the in circle. So, the in circle is this one here. We know that the sides of this triangle are, so this is 3, this is 4, 4 and this is 5 and 5. So, this triangle, the sides of the triangle are 7, 8 and 9, and therefore, we can use the formula for the in center. The formula for the in center is the area divided by the semi perimeter. The area, well, the semi perimeter is half of the perimeter, which will be equal to 8, sorry, that will be equal to 12. So, the semi perimeter will be equal to 12. The area is equal to square root of S into S minus A into S minus B into S minus C. Therefore, the in radius, which is equal to the distance of the point of intersection of the tangents to the point of contact, is equal to square root of 12 into, so 12 minus, let this be A, B and C. So, 5 into 4 into 3 divided by S. So, this will be equal to square root of 5 into 4 into 3 over 12, which is equal to square root of 5. So, the answer is that this distance from the point of intersection of the tangents to the point of contact of the circles is equal to square root of 5. So, this finishes the solution to this problem. Let us take the next problem. So, in this problem, it is said that we have a triangle ABC whose circumcenter is denoted by the point O and whose in center is denoted by the point I, and let R and R be the circumradius and the in radius respectively. So, now we have been asked to show that the square distance between the circumcenter and the in center is this quantity. So, note that the circumcenter and the incenter are not always the same point. In generally they are different points. So, in this question we have a triangle ABC as is drawn here, and it is said that the points O and I are the circumcenter and the incenter respectively. The circumcenter is constructed by drawing all the perpendicular bisectors of all the three sides, and the point of intersection of the perpendicular bisectors is the circumcenter. So, let us construct the let these be the perpendicular bisectors of the three sides, and they intersect at this point O. So, the point O is the circumcenter. The incenter on the other hand is given by the point of intersection of the angular bisectors of the three angles. So, let us now draw the angular bisectors of the three angles. So, this is the angular bisector of the angle B. Let us say that this is the angular bisector for the angle A, and this is the angular bisector of the angle C. So, let us say that they intersect at this point I, which is the incenter of the triangle ABC. So, the question is asking us to prove that it's basically asking us to prove that the squared length of this line segment OI, which is OI square. So, it is asking us to show that this OI square is equal to R square minus 2 R. So, this is what we have to prove, and as we see, we have to find the squared value of this the squared length OI in terms of the circumradius and the inradius. Clearly, if we let's join B and I and also B and O, and since O is the circumcenter, we can also draw the circumcircle, which will look something like this. So, let us say that this is the circumcircle. As we can see, the circumcircle is touching all the points A, B and C of the triangle ABC with O as its center. Let us also join O and, so this is C. So, let us also join O and C. Now, from high school geometry, we know that since this is angle A, this entire angle has to be twice of A. So, ultimately we are interested with the square of this length IO. So, we will be focusing all our attention on this triangle BIO, and the way to solve this problem will be to first find the value or the expression for this angle, and then also the length BI and the length BO, and then use the cosine of B formula, the cosine formula for angle B. So, that should help us to get this length OI. And that is because in this triangle BIO, so in the triangle BIO, cos of B is equal to BO. So, BO is, so this BO is actually the circumradius R. So BO square plus BI square minus IO square, this whole thing divided by 2 times R times BI. And therefore, if we rearrange the terms, we get that IO square is equal to R square plus BI square minus 2 times R times BI times cos of B. So, if we are able to somehow find R, BI and cos of B, then we should be able to find IO square. So, that is our strategy here for solving this problem. Let us now drop a perpendicular from this circumcenter. So, let us drop a perpendicular like this. So, note that this perpendicular, of course, this perpendicular is basically along this dotted red line, which was the perpendicular bisector of this line segment BC. So, now what we see is that if we consider these two triangles, which is B, so let us say that this point of intersection or basically this point where the perpendicular from the point O meets the line BC is the point D. So, this point is D. So, we can show that the triangle BDO and the triangle ODC are congruent, because OB is equal to OC is equal to R, because OC is also circumradius. Then we of course have a side in common, and then also this and this angle are the same, and therefore it follows that this angle BOD has to be equal to the angle COD. And since this entire angle was 2A, it follows that angle BOD should be equal to half of twice of A, which is equal to A itself. And hence this angle D, so angle DBO will therefore be equal to, since this is 90 degrees, it will be equal to pi by 2 minus A. Since this line BI is an angular bisector of angle B, it follows that this entire angle is B by 2, and therefore this little angle OBI of this triangle OBI is equal to B by 2 minus of angle DBO. So, this entire B by 2 minus this angle DBO. So, it is B by 2 minus pi by 2 minus A. Now, since in a triangle pi is equal to A plus B plus C, if we use A plus B plus C instead of pi, what we get is that angle OBI equals B over 2 minus A plus B plus C over 2 minus A, and upon simplification this is equal to A minus C over 2. And then of course we have to find, so far we have found the value of angle OBI. So, there's a little correction here, that when we were talking of this triangle BIO, so when we were talking of the triangle BIO, so then it won't be cos of B here, it will be cos of angle OBI. And therefore, here also we have cos of angle OBI. So, we have already found angle OBI, so we are going to use that here. We still need to find an expression for this length BI. For that, we drop a perpendicular from the in-center I to the side AB, then clearly this length is equal to the in radius r, and since this angle is b by 2, it follows that bi is equal to r over sine of b by 2. But since angle OBI has been expressed in terms of A and C, angles A and C, we would like to, instead of having sine B by 2 here, we would like to have some expression which is in terms of angles A and C. We already know that the in radius small r is equal to 4r into sine of A by 2 into sine of B by 2 into sine of C by 2. So, this is already known to us, and therefore, r over sine of b by 2 is actually equal to 4 into r sine A by 2 into sine C by 2. And therefore, we will use this expression instead of bi. So, this is equal to bi, and we have already shown that angle OBI is equal to A minus C over 2. And from the cosine formula, we already know that IO square is equal to r square plus bi square minus 2 rbi into cosine of angle OBI, which is equal to r square plus, so instead of bi we will use this expression, so it becomes 16 r square sine square A by 2 into sine square C by 2 minus 2 into, so 2 into r into bi. So, again for bi we use this expression, so it becomes 8 r square into sine A by 2 into sine C by 2 into cos of, so angle OBI is A minus C by 2. So, it becomes cos of A minus C over 2. Hence, IO square can be written as equal to r square into 1 plus 8 sine A by 2 into sine C by 2 times 2 sine A by 2 into sine C by 2 minus cos of A minus C over 2. Of course, here we have to use the 2 sine A sine B type of formula, and using that we will get IO square to be equal to r square into 1 plus 8 sine A by 2 into sine C by 2 times. So, now this is equal to cos of A minus C, because we are using the formula that 2 sine x sine y is cos of x minus y minus cos of x plus y. And therefore, using that formula, we get this to be equal to cos of A minus C over 2 minus cos of A plus C over 2 minus cos of A minus C over 2. So, these two terms get cancelled, and finally what we get is that IO square is r square into 1 minus 8 sine A by 2 into sine C by 2 into cos of A plus C over 2. But we know that A plus B plus C is pi, and therefore A plus C over 2 is pi over 2 minus B by 2. And therefore, IO square is r square into 1 minus 8 sine A by 2 into sine C by 2 into cosine of pi by 2 minus b by 2. But cosine of pi by 2 minus b by 2 is sine of b by 2. Therefore, using that result we finally get sine b by 2 here. But we already know that the product of the sine of half angles. So, this particular quantity here, we already know that it is equal to, if we go back to the previous slide, from here we know that this product is equal to r. So, this thing is obviously equal to r upon 4r. So, if we use r upon 4r over here, we eventually get this to be equal to r square into 1 minus 2r over r, and that is equal to r square minus 2r. And this finishes the proof of this problem. In the next lecture, we will discuss about the orthocenter and the centroid of a triangle. Thank you.